today we are happy to welcome our today's speaker, Professor Bharat Vishnu Ratra, who studied physics at the Indian Institute of Technology, graduating in 1982. Then he moved to Stanford for a PhD, and after several postdocs at some of the most famous institutes, including SLAC, Princeton, Caltech, and MIT, he became a professor at the Kansas University in 2004. As the title may suggest, the topic of his research is theoretical cosmology and astroparticle physics, and now perhaps he can.
Thank you. It's really nice to be invited here, and it's a great pleasure. So I'm a cosmologist, and I study the structure and evolution of the universe. And it's a very exciting time to be doing this because you're all familiar, I guess, even with the James Webb Space Telescope. And there's a lot of other really nice telescopes, both on the ground and space, and they're getting lots of good measurements. And they're confirming two very, very striking results. So the first one, most of you are probably quite familiar with this. When you go and look at what's powering the expansion of the universe, we find we only understand 5% of the material there. So 5% is the atoms and molecules that we're very familiar with, and the remaining 95%, all we're seeing is the gravitational effects of it, and it's divided into two parts. One's called dark matter, the other's called dark energy. And so there's lots and lots of things to be understood about dark matter and dark energy, and that's what makes it so exciting a time in cosmology. The second result that's kind of getting reinforced is that these cosmological observations are indicating that either quantum mechanics or relativity or both are incomplete descriptions of reality and need to be improved upon. And if that holds up, then it's going to be a really exciting result because quantum mechanics and relativity have been the foundations of physics for more than a century. So some of you, or many of you have probably heard we're doing precision cosmology now. And it's kind of instructive to go back and look at other periods in physics where people have felt the same way. So I'm going to go back. I'm not meaning to imply that cosmology is solved now, but I don't think that we have a problem with the standard model. I think the skeleton is in place, and we need to fill in a lot of details that are quite important, but I don't think the skeleton is going to be radically changed. So I went back to the end of the 1800s, and this is a quotation from a really famous physicist. Maybe I should probably just use this. I think maybe the battery is going. From Michelson, who invented the interferometer. And at this point, physics was Newton's three laws of motion and his inverse square law for gravity. And we have Maxwell's equations for electricity and magnetism. And Boltzmann had introduced the Boltzmann factor, but it wasn't very popular at this point. But Michelson says basically everything's over. All you have to do is go and do precision measurements. And I don't want to leave you with the impression that I'm biased against experimentalists. I went and looked for an equally famous theorist around the same time. And this is from Baron Kelvin, who lent his name to the absolute temperature scale. And he kind of says that there's nothing new to be discovered in physics. Now, all that remains is more and more precise measurement. And to be fair to him, he did mention the problem with the ether and the ultraviolet catastrophe. And the ether problem led to, in some ways, to the special theory of relativity, and the ultraviolet catastrophe was resolved by Planck's discovery in the same year. His explanation, Planck's explanation of black body radiation. And then a few years later, Einstein kind of introduced quantum mechanics through the introduction of photons and his explanation of the photoelectric effect. And in that same year, he introduced the special theory of relativity. And a few years later, we got Rutherford's model and Bohr's more accurate model of the atom. And that was quickly followed by all of quantum mechanics and general relativity. So we go from Newton's three laws of motion and his law for the inverse square law for gravity and Maxwell's equations to many, many new areas of physics, starting probably with condensed matter physics with Einstein's model for the solid, which he introduced to try to understand specific heat. And then we got all of atomic and molecular and optical physics, the beginnings of it based on Bohr's model of the atom. And then Chandrasekhar's use of the Pauli exclusion principle to explain the structure of white dwarfs was kind of the beginning of astrophysics. And in the 40s, we got the quantum version of Maxwell's equations, quantum electrodynamics, through the work of Tomonaga, Schwinger, and Feynman. And that was followed a decade, two decades or 2.5 decades later by the standard model for the electroweak physics and for QCD, the strong interactions. And I think something similar is going to be happening in this decade or the next decade, and we're going to have a pretty big change in physics with the standard hot Big Bang model of cosmology. And that's what I want to be talking about mostly in this talk. So I'll start with the energy budget now to the present energy budget. The fractions change because things are evolving. And so we know that 5% of the material out there is what cosmologists refer to as baryonic matter. And this is basically atoms and molecules and charged particles like electrons and protons. And this was came out of the work that Gamow and Alpha and Herman did on trying to explain the abundances of the light nuclei. And they realized there'd be photons left over, and through a very inspired guess, they understood these photons could be in the microwave part of the spectrum at the present time. And people tried to look for that, but it wasn't until Penzias and Wilson in the 60s discovered this essentially by accident by doing more and more precise measurements. And their paper was accompanied by a companion paper by Dickey Peebles, Roland Wilkinson, explaining the significance of their observations. And this number started getting pinned down more like in the 70s or so, 80s. Even before that, Zwicky was looking at clusters of galaxies. These are collections of galaxies that are in gravitational orbit around each other. And he could measure how fast these galaxies were moving. And he assumed that this motion was caused by the gravitational field of the mass there. And so he could figure out how much mass he needed to produce the speeds he was seeing. And from that, he could deduce that there was much more mass than there was in the shiny material in these clusters of galaxies, more mass than there was in stars and in hot gas. So he ended up discovering dark matter because it wasn't shiny. And the speeds he was looking at was hundreds to thousands of kilometers per second, which is much, much smaller than the speed of light. And so that's non-relativistic, and it's also referred to as cold. And Zwicky didn't know that there's only 5% baryonic matter out there. He didn't know the amount of baryonic matter. And this number started getting pinned down much later in the 70s and 80s. And people realized that there was a new kind of matter there, or maybe many new kinds of matter that's not related to atoms and molecules. And even more recently, people have discovered something that they've called dark energy. And this is just a name. This energy is being used as a name here. It's not energy in the sense of mechanical energy or kinetic energy or electromagnetic energy. It's a name to distinguish it from matter. And it's also dark because we don't see any light being emitted or absorbed from it. And unlike the cold dark matter, if it's made up of particles, these particles are moving very, very fast. They're very light particles, and they're moving at speeds almost at the speed of light. And it's not baryonic, and it's by far the biggest contributor to the energy density of the universe now. So we basically don't know much about the 95% of the stuff that's dark matter and dark energy. And that leaves a lot to be discovered and understood. So it's a really exciting time now in cosmology. So I'm going to try to develop this model, the standard model of cosmology based on observations and theory. And then if I have time, I'll look at inflation very early on in the universe. That's supposed to have happened when the universe was maybe 10 to the minus 33 seconds old. It's probably 13 3/4 billion years old now. So that's something that happened very, very early on. And that's where all the structure we see both in the electromagnetic radiation and in the matter fields was developed from quantum mechanics. And if we have time, we'll go over open questions. So we're going to talk about this hot Big Bang model, and it's a model that applies at late times on very, very large scales, and it describes the dynamics of the obvious parts that you're probably more familiar with are the matter and radiation, but it also describes the dynamics of space-time. And because it's on very, very large scales, we're not going to use centimeters or meters as our length units. I'm going to use parsecs, and roughly that's 3¼ light years, or in terms of centimeters, if you wanted, here's the conversion factor. The smallest objects I'm interested in are galaxies like the Milky Way we live in. So these are typically collections of many millions to billions of stars, maybe even tens of billions or hundreds of billions of stars. And they're rather large. If you kind of think of it as some typical radius, then it's between 1 and 100 kiloparsecs. So galaxies, because they're so massive, if they come close to each other, they can kind of get into orbit around each other, and they found gravitationally bound structures called clusters of galaxies. And the scale here is a few million parsecs. And there's a couple of other scales which I'm going to skip, and then eventually you get to the Hubble length, which is the distance over which light can travel in the age of the universe. So it's the observable part of the universe. And it's roughly maybe 30, 40 billion light years away from you, even though the universe is only 13¾ billion light years. That's because of the expansion. And when you account for the expansion by doing the integration, then you get out to an observable radius of 30 or 40 billion light years, depending on the model you're looking at. So we can look at how matter is distributed in space. And this is from the Lick Observatory observations of Shane and Virtanen. And if you look at it, it's a pretty big chunk. So the scale here is 300 megaparsecs, about 1 billion light years across here. And you can see three kind of distinct structures. You can see clusters of galaxies. That's the Coma cluster. You can also see regions where there's hardly any bright galaxies, and these are called the voids. And then you can see one-dimensional filamentary structures, and these are called filaments. So this distribution looks very different in different directions. It's anisotropic, just like this room is anisotropic. If you look to your right and you look above you and you look below you, you don't see the same person. It looks different in different directions. But when we get out to larger scales, so locally on the scales of hundreds of millions of light years, matter is distributed in an anisotropic way in space. But when you get out to much larger scales, like billions of light years, the distribution becomes isotropic. It looks the same no matter what direction you look in. And we can skip these numbers for now. Maybe I'll come back to them later. But once we know that we're seeing everything looking isotropic around us, you can then just use the same logic that Copernicus used for moving the center of the solar system to the sun, that we're not privileged observers, and an observer on some other galaxy should also see things looking isotropic. And that means that we are living in a homogeneous distribution in space. So when you say something's homogeneous, that means you move from one place in space to another place in space, and you look around, and it looks isotropic again. And this distribution has much more symmetry, and it's more symmetrical than a distribution that's isotropic about one point. And this is a very important foundation of cosmology, so I'm going to spend a bit of time trying to justify this. So what we're going to look at is a bunch of different measurements, and what we're looking at here is these infrared bright galaxies. These were taken with the infrared detector on the IRAS satellite. And so we're in here looking out with an infrared detector, and we're looking out to a certain distance. And the distance we're looking out to is 45 megaparsecs. So I'm looking at the interior of a sphere of radius 45 megaparsecs, and I'm plotting all the bright infrared galaxies. So I sliced the sphere from the North Pole to the South Pole and opened it out. And if you want to fold it back up, you can take this edge and merge it with this edge and fold it back up. And the smaller guys further away, the bigger guys are close by. And this is the plane of the Milky Way, so it kind of blocks some of the light. So that's not extragalactic space there, so it's kind of obscured. But above the Milky Way and below the Milky Way, what you're seeing is stuff that's some distance away from us. And you can see it's a pretty anisotropic distribution. You look over here, there's a void. You look over here, you see a big cluster with many, many galaxies. And we can go out from 45 to double the distance. We go out to 90. And because it's a sphere, the volume increases by a factor of 8. But I've taken out the central 45. So what you're seeing is a volume here 7 times bigger than the volume I showed you here. And you're starting to see many more clusters, and the voids are starting to fill in because you're seeing the stuff behind them. And we can go out even further to 300 megaparsecs, and the distribution is starting to get much more isotropic. So compared to this distribution locally, it looks very different in different directions. Here it looks much the same no matter what direction you look in. You take a big enough area, you'll get about the same number of galaxies. And if you go out to larger scales, you need to see brighter objects. So we're looking at X-ray sources. These are black holes or very big stars that are very hot. And the Milky Way is over here. But as long as you avoid the Milky Way and avoid local sources, that's a black hole in M87. These are the large and small Magellanic Clouds. But in regions that are not contaminated by local X-ray sources, the distribution is pretty smooth. It's smooth to 0.1%, so it looks roughly the same here and here and here. And you can go out and look at even brighter sources or larger scales. And this is the microwave background. So this is what was taken by the Planck satellite, the European Space Agency one, and they had microwave detectors on it, so they're looking at the afterglow of the Big Bang. And these are microwave background photons that have come from the Big Bang to us. So again, you're looking out in all directions. And they're measuring the color or the spectrum or the temperature. And what they have here is an average that you can just, the first thing you might be interested in is the average temperature across the whole sky. And that's about 2 3/4 Kelvin. So it's quite cold. So Kelvin's the absolute temperature scale. This room is around 300 Kelvin. So it's very, very cold compared to this room. And then the next thing you might want to ask is the difference between the red hot spots and the blue cold spots. And that temperature difference is 30 or 40 microkelvin. So delta T is maybe 30 microkelvin. T average is 3 Kelvin. So delta T over T is 30 microkelvin divided by 3 Kelvin. So it's 1 part in 10 to the 5 or 0.001%. So the temperature over here is the same as the temperature over here, differing by only 0.001%. So it's pretty isotropic. It differs only by 1 part in 10 to the 5. But if you go back over here, it's much, much more bumpy. It looks different in different directions. So those are 2 of the really important facts about the universe, that locally matter and radiation is distributed in an anisotropic way in space. And on large scales, if you get to larger scales, over hundreds of millions of light years, the distribution is isotropic. And if we have time, we'll see how physicists explain this in the inflation model of the early universe. But if I don't have time to go over inflation, you can find this on your favorite search engine. Just look for inflation model of the early universe. And Wikipedia has good articles. You have to be really careful what you read on the web. But if you go to Wikipedia or Scientific American, and there's probably equivalent sites over here that you can look at that have good descriptions of the science. So the next thing we want to talk about is the expansion of the universe. Excuse me. And when we say this is expanding, that immediately implies that we've got measuring devices that are not also expanding. And so it's kind of useful to understand how those measurement devices are not expanding. So the typical measurement device we can use is a meter stick, and we know that meter sticks are made up of atoms or molecules, and that's governed by the electromagnetic force, which is a much, much stronger force than gravity. So if you take two protons, they're going to be attracted by gravity but pushed apart by the electric force. And the ratio of that electromagnetic repulsion is 36 powers of 10 stronger than the gravitational attraction. So as long as you're thinking about meter sticks and things on scales on which electromagnetism is important, gravity is unimportant because electromagnetism is that much more stronger than gravity. But when we get to bulk size objects, they become neutral, basically because we're made up of molecules or atoms and we have an equal number of electrons and protons. And so when we're looking at very large objects like planets, for instance, they're mostly neutral, but they're much more massive. So the gravitational force is much, much stronger there because the electromagnetic force is screened. So the electromagnetic force holds the meter stick together. And on really large scales, when you have very massive objects, gravity is going to be the dominant force. And so we have to use the most accurate model we have for gravity, which is Einstein's model of general relativity. And in that model, it says that gravity kind of wanders around and it looks for regions in space where there's less mass and it creates new space. So Einstein's general relativity improves on Newton's inverse square law by making space and time be part of the dynamics. And so it can describe phenomenon more accurately when you have strong gravitational fields, or you're talking about things on very large scales, or you're talking about things that are moving at close to the speed of light. And so what it does there, it kind of creates this new space, and everything lives in space, and space kind of spreads out. And it takes everything along for the ride. So we can, oops, I don't know. Okay, so it's come back. So we can maybe just start with this little toy model of a universe here. So it's a one-dimensional universe. It's the circumference of a circle. And this is it at an early time. This is it at a later time. And I've drawn the radius here. I'm going to call this A of t, and it's very loosely the scale factor. It tells you the size of the universe because the circumference is 2 pi times this radius. And as time gets bigger, the circumference gets bigger if it's an expanding universe. And it's also 2 pi times the new scale factor. And I've also put an electromagnetic wave on it here. So you can think of this as a light wave, and the time period there is femtoseconds or tens of femtoseconds, while the expansion time, this time over which the universe doubles in size, is roughly the age of the universe, which is 13.75 billion years, which is roughly an exasecond. So the difference between the time period associated with the wave and the time period associated with the expansion is maybe 33 orders of magnitude. And so a situation like this is said to be adiabatic. You have these two very different time scales, and you can't pump energy from the wave into the expansion of the universe, or you can't pump energy from the expansion of the universe into the wave. And so your only option is the number of zero crossings have to remain the same. And if the number of zero crossings have to remain the same, the wavelength has to increase. And that's the signal we're going to see. So it's pretty easy if you just draw this, and you can see that the wavelength is going to go in proportion to the scale factor. And so if you start out with blue light, as time goes on, it becomes more and more red, and then eventually it'll become infrared. And astronomers don't work with the scale factor. They instead work with something that they call the redshift, or this variable z or z. And it's defined as 1 plus z is equal to the scale factor now divided by the scale factor at the time at which the light was emitted. So if we go over here and we emit the light over here, that'll be A of t. And if we go to look at the light here, this will be A of now. And so if we go back over here and just look at the redshift at the present time, then t would be t now, and a now would be divided by a now. This would be 1, and the redshift would be 0. But as you go back to earlier and earlier times, a gets smaller than a now, and the redshift gets bigger. And so when you look at a diagram like this, what you're seeing is that time increases this way. So early times are when the universe is smaller, late times are when it's bigger. And the scale factor also increases in this direction. At late times, the scale factor is bigger. But as you go back in the past, the redshift becomes bigger. So redshift increases towards the start of the expansion. Scale factor and time increase towards the end of the expansion. And this was discovered by Slipher. He was looking at galaxies outside the Milky Way, and he discovered this in 1912. What Slipher was looking at, he was just pointing his telescope at galaxies outside the Milky Way, collecting the light, passing it through a diffraction grating, and identifying spectra, and he realized that their wavelengths were redshifted. And so one possibility is that there was a big explosion right where he was, and everything was moving away from him, and this explosion happened before Slipher showed up. But that's not what's happening. It's something even more interesting. And I'll try to use this cartoon description to illustrate the proper explanation of Slipher's observations. So we're going to start out with a three-dimensional flat universe. So this universe here is a one-dimensional closed or compact universe, because all you need to know is your position along the circumference. But over here, it's a three-dimensional universe because there's a vertical dimension, three spatial dimension, a vertical dimension, and two horizontal space dimensions. And I'm going to look at a little chunk of it here. And it's clear this has to only be a chunk, because if it wasn't a chunk and it was actually the complete universe, you could go to the edge and look out, and it would look different than when you were looking in, so it wouldn't be isotropic. And we argued that the observations tell us that the distribution is isotropic on large scales. So this has to extend to infinity in all three dimensions. And I've put chocolate chips in here. These are my galaxies, and I'm going to let the yeast rise. And as it rises, it gets bigger and bigger. And we can ask an observer on each of these chocolate chips what she sees. And she's going to tell us, so if we put an observer on chocolate chip 2 and ask her what she sees, she's going to say every other galaxy is moving away from her. And you can go to an observer on number 4 and ask him what he sees. He'll say every galaxy is moving away from him. So even though Slipher saw every galaxy moving away from him, that didn't mean he was at the center of the universe and everything was moving away. But any observer is going to see every galaxy move away from them. And this is really what's happening. So at some instant of time, every point in space starts moving away from every other point in space, and that's the Big Bang. And this continues, and that's the expansion of the universe. So one-dimensional things like proper lengths and wavelengths, they're going to expand in proportion to the scale factor, but the volume here, because it's 3 dimensions, each dimension expands in proportion to the scale factor, so the volume goes like a cubed. And that's the expansion of the universe. So in 1929, well actually in 1926 or so, Hubble had access to a better telescope, a bigger one, and using his telescope he could actually see individual stars in these galaxies that Slipher was looking at. And he identified some pulsating stars, which he realized were Cepheid variable stars. And these stars are very important because of a discovery that Henrietta Leavitt had made in the early 1900s. She'd figured out that the period of pulsation of these stars is very, very regular because there's an instability and it's a very regular pulsation. And the period is related to the wattage of the star. So once you know the oscillation period, you can figure out the wattage of the star. And once you know the wattage of the star, you can use the intensity inverse square law relation for electromagnetic radiation. and that'll give you the distance to the star. So Hubble was able to measure distances to these stars, and he realized with Slipher's measurements of the redshifting, you could use the Doppler formula and you could get the speed, that there was a very nice relation between the speed of recession and the distance, and it was a linear relation. So a galaxy that was twice as far away from us would be moving twice as fast. A galaxy that was 3 times as far away would be moving thrice as fast, and so on. And this constant of proportionality is the Hubble constant. And it's got strange units. You can figure out the dimensions very easily. This is distance over time, and this is distance, so the two distances cancel out. And h naught has dimensions of 1 over time. But because astronomers measure the distance in megaparsecs and they measure the speed in kilometers per second, the Hubble constant has units of kilometers per second per megaparsec, but its dimensions are 1 over time, and very roughly it's the inverse of the age of the universe. And you have to be a little more careful because the expansion rate isn't constant. But this law is true at any time during the age of the universe, during the expansion, except the constant depends on when you apply this law. And so when you're using this at earlier times or at later times, you call the constant of proportionality the Hubble parameter. And at the present time, that constant is called the Hubble constant. So we can see where this comes from. It's very, very easy to derive this once you know that you have a homogeneous universe. So let's look at a two-dimensional flat universe. So it's 2 dimensions because it's on an XY grid here. So if you set up your origin, you just need to know 2 coordinates to figure out which galaxy you're looking at. So this is it at an earlier time. This is it at a later time. And so I've gone from galaxies that are 100 megaparsecs apart to letting them expand so they're 150 megaparsecs apart. And we can measure the distances. So the original distance between A and B is 100 megaparsecs. A and C is it's 200 megaparsecs. A and D is 300 megaparsecs, and so on. And the final distance between A and B is 150, and then A and C is 300. And so we can make a table here. We can subtract final minus initial. We get 50. Final minus initial is 100. Final minus initial is 150. And so the change is 50, which is half of 100, 100, which is half of 200, 150, which is half of 300. So this is delta R, and this is R. So if we go back to what we have here, this is delta R over delta T, and this is R. So delta R is proportional to R if you're looking at 2 times, and delta T is a constant. And you can see delta R is proportional to R. So this is Hubble's law. It's just telling you get uniform expansion in a homogeneous distribution in space. So the increase in distance is proportional to the initial distance, and that's Hubble's law, and it's very simple to derive that. And you can see that this is supported by the observations. This is a famous plot from the final Hubble Space Telescope Key project to measure the Hubble constant, which was led by Wendy Friedman. And the recession velocities of the galaxies are on this axis. The distance is on this axis. The numbers are down here. These are residuals. We can forget about this panel for now. But if we go to a galaxy 100 megaparsecs away from us, that galaxy is moving away at about 7,000 kilometers a second. 200 megaparsecs is about 14,000 kilometers a second. And this solid purplish line here is the best fit to these measurements here. And so that just tells you that the recession velocity is proportional to distance. And the Hubble constant is just the slope. So in 2001, it was around 72. I think my favorite value is around 68 now. And we can look at, so there's some issues about what exactly the precise value of the Hubble constant is now, and this is sometimes called the Hubble tension. And this is an example. So some measurements give us something around 74. And the blue one's my favorite value, around 68. So these are numbers from a decade ago. And so what we're looking at here is a bunch of different measurements. So there's microwave background measurements, both on large angular scales and on small scales. And then galaxy clustering measurements. And we're going to fit them to a cosmological model and integrate over all the other free parameters except the Hubble constant on this axis, and then the number of relativistic neutrino species. So we know in the standard model of particle physics, there's three neutrino species. There's the electron, mu, and tau neutrinos. And depending on how they decouple, they're effectively a little bit more than 3, so it's around 3.045 or so. So we're going to use these guys as priors for this analysis. And we see with the red contours with 74 or 73.8, 1 sigma favors around 4, and 2 sigma also doesn't come to the standard model of particle physics number of neutrinos. But the 68 one intersects that even at 1 sigma. So you can conclude from this that the standard model of particle physics is happy with 3 neutrino species, and cosmology is happy with that, provided the Hubble constant is 68. But if you have a Hubble constant of 74, one way is to introduce an extra neutrino species. But this kind of seems unlikely at the present time. So we have the expanding universe. And then there are observers in this universe, and the observers that are at rest with respect to the expansion will see that it's isotropic, and those are the guys who live in the homogeneous distribution. But if you have an observer on a rocket moving, that observer will see the Doppler effect in the front and back, and the sides will look different. And that observer, she won't see that it's isotropic. So we have to be careful and always focus on these guys called cosmological observers. These are observers that are at rest with respect to the expansion. And we've then generalized the Copernican principle to the cosmological principle that all such cosmological observers will see that the universe is spatially isotropic. And so if you translate yourself in space, you go from here to Andromeda and ask what an observer there would see, and she would see something on large scales that's isotropic too. And that means that we're living in a homogeneous distribution. And that makes our life more simple, because then there are only 3 possible geometries: the flat, open, and closed Friedman, Lemaitre, Robertson, Walker models. And so we're discussing the spatial part. So there's a vertical dimension and 2 horizontal dimensions. So to know where you are, you need 3 coordinates. And I can't draw those 3-dimensional spatial geometries, so I'm going to suppress one space dimension, and I'll just show you the 2-dimensional analog. So we'll start out with the flat one, which is like the top of this table. But again, there can't be an edge, because if there was an edge and you looked out, it would look different than when you looked in. So the flat case has to go to infinity. And for those of you who know some general relativity, here's the line element. And this is the curvature scale factor. And then you have the expansion of the universe scale factor. So this is flat. It has 0 curvature. Then you have the closed one, and it's the surface of a sphere. And as time goes on, this gets bigger and bigger and bigger. And so the way you think about this is you think about being an ant on this surface. There's nothing inside, there's nothing outside, but as time goes on, the surface gets bigger, and by doing local measurements, you can discover that expansion. And this is positively curved, and it's closed, and it's also compact, but it's called a closed model. And then you have the open model, which is saddle-shaped, but you've got to go out to infinity in both dimensions, otherwise it won't be isotropic. And that's got negative space curvature, and it's called open. And there's this parameter omega. This is just the density of matter. I'll explain it in a second. This flat case has critical density. Omega naught is equal to 1. This is an overdense model, omega naught is greater than 1. This is an underdense model, omega naught is less than 1. And we can go and look at, so the dynamical variable, it's probably easiest to think about it here. You can think of it as the radius, and that would be the scale factor. And so this is just like any other physical system. You need an equation of motion. And if you think about the harmonic oscillator, you have a mass and spring, and the displacement from the equilibrium is your dynamical variable. And you can call that x, and that the equivalent thing here is the scale factor. So instead of writing down ma equal to f for the harmonic oscillator, so that would be mx double dot is equal to f, and if you put a Hooke's law force, it'll be mx double dot is equal to minus kx. You can integrate that once, and you'll get conservation of energy, which is 1/2 mx dot squared plus 1/2 kx squared equal to constant. And that's the equation I'm going to write down here. And this comes from general relativity, so I'm going to make some assumptions. So I'm going to start out with the matter fluid. And we don't want to talk about the mass of the whole universe, because the universe could be infinite, and then its mass is going to be infinite. And so when you're trying to discuss the gravitational field of the whole universe, you start having problems. So you look at a local patch of the universe and look at the amount of mass in there and look at the mass density there, and that's what's going to be responsible for the local gravitational field. So I'm going to be working with this variable rho, which is the mass per unit volume, and I'm working in natural units where I set the speed of light equal to 1. So what we have here is a dot, that's a time derivative, and a is the scale factor. And if you want to think of it in this model, it's just this radius. As time goes on, it gets bigger. So this is a dot, it's dA dt, the rate of change of the scale factor. And this is the energy associated with the expansion. Then G is Newton's big G, because that's the gravitational force. And it's what's powering the expansion, and it's the mass that gives you the source of the gravitational field. So this is from the mass, rest mass energy, basically. And you can get some energy from the curvature of space, and it comes in with the curvature divided by the scale factor squared. And I've also put in a cosmological constant, which is a constant that's independent of space and time. And unlike the 1/2 mx dot squared plus 1/2 kx squared, which you can easily integrate for the harmonic oscillator, you can't do that here, because as space expands, the volume gets bigger and the density drops, and so you need to know how that changes with time. And that comes from the first law of thermodynamics. This is just the rate of change of the energy density is equal to PDV work. And so we introduce pressure, and to complete this, you need an equation of state. And if I wasn't using natural units, this P would come with the C squared in the denominator, and this is just an effect of the relativistic effect, and that's what that C squared is telling us. So we know that the expansion rate, which is just A dot over A, which is the Hubble parameter, is positive because everything's moving away from us, everything's redshifted. So the next thing we might be interested in is whether this increases or decreases with time. And the easy way to think about this is to do some calculus. You differentiate this equation once and use these other two equations, and then you can get an acceleration equation, which is 2 time derivatives of the scale factor. And it's just kind of unfortunate that in F equal to ma, the acceleration is also a, and I'm also using a for the scale factor, but that's the convention both in cosmology and in Newtonian dynamics, and I'll never use a for acceleration here. So my acceleration is always a double dot, and a is the scale factor. So this is the a part of the f, a equal to f over m equation, and this is the f over m part. And you can kind of see what's going on over here. So if we just ignore all these guys for a minute, you can see this is due to the gravitational field, and this is the mass, rest mass energy. And it's pretty easy to understand what's happening. If you have two galaxies near each other, Newton will tell you they're going to pull on each other and they're going to overwhelm Einstein's space creation process if they're really massive. And that's what this negative sign is telling us, that the mass density is going to give you deceleration. A double dot is negative. Now, if you have galaxies that are also moving, they'll have a pressure. The particles of this fluid are the galaxies, and the deceleration is also going to be larger. And so you kind of think you're going to predict that there's only going to be a deceleration, and so you can ask your observer friends to go out and measure A double dot, and they actually find that it's positive, there's acceleration. So you're left with two alternatives. Either you say Einstein was wrong and these are the wrong equations and so we don't have a problem, or we can say that we're missing some substance in the universe and we want to introduce that into Einstein's field equations. And so I'm going to introduce a cosmological constant here, and it's also going to have a mass density and a pressure, but it has a strange equation of state. Its pressure is minus its energy density. And if you have rho lambda plus 3p lambda, and p lambda is minus rho lambda, then this is minus 2 rho lambda. And if rho lambda is much bigger than rho matter, this can dominate, and everything inside the square parentheses can be negative, and that'll cancel this negative sign and give you acceleration. And that's why dark energy is introduced, because we want to preserve general relativity, and we know this side is positive, and so we need to make the right-hand side positive. And so I was talking a little bit about this parameter omega. So this is for when you throw away the curvature and the cosmological constant, you can see that the energy density is completely determined by the Hubble constant. So that's the Einstein de Sitter model, where you don't have curvature and you don't have lambda. And then the Einstein de Sitter energy density is this. It's roughly 10 to the minus 29 grams per cubic centimeter. And so instead of working in grams per cubic centimeter, one uses this as the unit and defines omega to be rho divided by rho Einstein de Sitter or rho critical. And so that's just a way of measuring the energy density. So the next thing I want to do is kind of look at all the components of rho and curvature and lambda in the universe, and then look at that whole equation with all the details. So we'll start out with the shiny stuff. So if we look at the shiny stuff, that's the stars and hot gas. Then omega luminous is very, very tiny. It's 1/2 of 1% or so. So the other thing you can do by looking at things in motion, you can measure the mass that's enclosed, that's causing that motion. And you're familiar with measuring the mass of the Earth by looking at how the moon moves around the Earth or how a satellite moves around the Earth. And you do the same thing here. You use Newton's inverse square law for gravity, and you take a circular orbit, and then the acceleration is just v squared over r. And then you can get the v squared related to the mass inside that's causing that motion through the gravitational field. And you can measure that mass, and then you divide through by rho critical, and you get the omega. So if you do this using 21 centimeter hydrogen radiation, you get somewhere between 20% and 35% of critical density. And these are examples of different spiral galaxies. So the velocity, the rotational velocity rises as you move away from the center, and then it flattens out. And we don't see the Keplerian 1 over square root of r drop off. So if this mass was not radius dependent and it was just the shiny stuff, it would eventually asymptote to a constant, and then v squared would be proportional to 1 over r, and so v would be 1 over square root of r and would drop away. But this is not asymptoting to a constant. It's rising even when you've gone beyond the shiny edges of the galaxy, because you can see the hydrogen gas clouds outside the shiny visible part of the galaxy through the 21 centimeter radio radiation. And you can go out all the way to hundreds of kiloparsecs using different techniques. And omega is always in this range, roughly. So we can look at the speeds. It's a few hundred kilometers a second. So there's hardly any kinetic energy. It's mostly rest mass energy. So rho dynamical, the density of dynamical stuff, is mass divided by volume. Volume increases with the third power of the scale factor. And if you take these numbers and plug in over here, it's a few times 10 to the minus 30 grams per cubic centimeter. But as the scale factor gets smaller, the universe becomes denser because this gets larger and larger. So the other thing that's out there now is the black body radiation left over from the Big Bang. I showed you the pictures. This was the first telescope that detected it. And this was the first satellite that did a very good measurement of the spectrum. And here's the spectrum. The intensity is a function of wavelength up here and wave number down here. And these are the data points. And this is just a black body that's fit at 2.725 Kelvin. And these data points, the error bars are 400 sigma error bars, so you can see them. So it's a very, very, very good black body. And once you know it's a black body, you can use the Stefan Boltzmann law. The rho, the energy density in the radiation is the fourth power of the temperature. And you get it to be about a few times 10 to the minus 34 grams per cubic centimeter, which is much less than this guy, the mass density, the non-relativistic matter. So it's subdominant, but at the present time, but you know from Boltzmann's formula that the energy of a photon is going to be the temperature times the Boltzmann constant. And from Planck's formula, the energy is Planck's constant times c divided by wavelength. The wavelength increases with scale factor, so the temperature drops with scale factor. So this fourth power of the temperature gives you 4 powers of the scale factor in the denominator. So instead of rest mass energy, it's E divided by c squared. And because E is proportional to frequency and inversely proportional to wave number, you get 1 extra power of 1 over scale factor. So this is 1 over 8 to the 4th. So as you go back in time, this gets smaller, the temperature gets hotter, and we can draw the energy density as a function of the age of the universe. So we live over here, and at early times you have the baby universe. So now you get the 1 over a cubed of matter, the non-relativistic matter, which is the atoms and the cold dark matter. And that's the radiation, the 1 over a to the 4th. So this is down by 4 orders of magnitude now. And the dominant, so I'm ignoring dark energy, I'll come back to that. But as you go back in time, the radiation becomes more important because the scale factor gets smaller, and there's 4 powers of the scale factor in the denominator compared to 3 now. So earlier on, it's radiation dominated. So I was going to talk a little bit about Big Bang nucleosynthesis, but I think I'll run over my time, so I'll skip that, and we'll just go straight to dark energy. And over here, I want to look at 2 different universes. So I'll look at one universe. So this is the Hubble law, distance against recession speed. So I'll look at a slowly expanding universe and a more rapidly expanding universe. So I'm going to go look at a galaxy at the same distance in both these universes. And so in the more slowly expanding universe, that galaxy will be moving away with a slower speed, while in the more rapidly expanding universe, it'll be moving away at a faster recessional velocity. And if you look at a galaxy further away, it'll be moving away with the faster speed compared to this guy. But it takes longer for that light to reach you. So when you're looking at a galaxy at a greater distance, you're studying it at an earlier time. So there's 3 possibilities as you go back in time and go out in space. It could be that the expansion rate was constant, like this purple line, Or it could be that this expanded more slowly in the past at a greater distance for you, like this blue line. And as you came to the present, the expansion sped up. Or it could be that in the past, when you're looking at galaxies that are further away from you than now, that in the past that it expanded more rapidly, and as it came to the present, the expansion slowed down. So this would be a decelerating universe, this would be an accelerating universe, this would be a universe at constant expansion rate. And in the 1990s, the things that we could use to look very, very far out were the type 1a supernovae. And when we did that, we found that they were all in the blue part of the diagram over here. And so we had an accelerating expansion. And some of you have probably seen plots like this, where you try to look at the amount of cosmological constant contributing to the energy budget and the amount of matter. So this is cold dark matter and baryonic matter. And if there was no accelerating expansion, you should lie on a line here at omega lambda equal to 0. But the supernovae force you up here, and it's about 3 sigma, and now it's probably about 4.5 sigma. This is from a decade ago, away from a non-accelerating expansion. So in terms of this acceleration equation, you need negative pressure overall to give you a positive acceleration, and that's dark energy. And so if we take the simplest dark energy model, which is Einstein's cosmological constant, we'll add in this green line over here. And we have to be a little bit careful because this is a log-log scale. So even though it looks, this green line is just barely above the blue line over here, it's actually a factor of 2 or so bigger it's almost a factor of 3 bigger than the blue line, because it's completely dominated by dark energy now. And this dashed line is probably when the universe is 5 to 7 billion years old. So after half the age of the universe, the cosmological constant takes over, you get accelerated expansion. Before that, dark matter and baryonic matter, and then earlier on, photons dominate, and they all have positive pressure, and they give you decelerated expansion. And you can see this in the data too. So this is some measurements of the acceleration rate at different redshifts. And I'm just going to combine these guys because it's dense enough so we can bin them together. And you can see that you get decelerating expansion down to a redshift of about 0.6 or 0.7 or 0.8. And then it starts accelerating. And the transition between when dark energy takes over is somewhere around 0.75 or so. So this is the accelerating part, this is the decelerating part. And I was going to talk about inflation, but I probably should stop because I'm going to run out of time. And we'll just go and review this. So at the present time, so we have maybe atoms and molecules. So this is slightly old, it's about 5%. And dark matter is about 25%, and dark energy is about 70%. But as you go back in time, you can see from our plot here that different things dominate. Dark energy dominates now, then dark matter and baryonic matter dominate during this part of the universe, then photons dominate here. So the ratio changes, and at the time, at the Big Bang, when things decouple and the photons start free streaming, dark matter is the dominant thing. There's neutrinos and there's photons and there's atoms, and the dark energy is very, very subdominant. So I'll just leave this up here. We have a cartoon. It's very, very strange that we have to have dark matter and dark energy. And we don't know what the dark matter is. We don't know what the dark energy is. But the cosmological constant does a really good job fitting the observations, and it's consistent with most things. But you can have mild time-varying dark energy, And that might be easier to accommodate in the rest of physics than a cosmological constant, because you can model dynamical dark energy using a scalar field, and we have a scalar field in the standard model of particle physics, and maybe a second one is not that big a deal. I mean, I think general relativity is okay, and I think the astronomers have really done a good job at pinning down all the errors that they need to find, and I think the observations are okay. So we don't know what the dark matter is, and maybe we'll start getting some hints from particle physics experiments or some of these deep underground mine experiments like the ones in the tunnel in Mont Blanc or at Grand Sasso or in South Dakota in the US. And some of the simplest dark matter models might already be in a bit of trouble. And maybe one way out is to couple the dark matter to the dark energy. But there's many, many issues. I mean, even after we've dealt with this, I'll just leave this up here. Cosmology won't be complete after we've sorted out dark matter and dark energy. And so there's a lot of things to do in the future. And I can put that up again later if people are interested. I'll just stop here. Thank you.